Continuando con la charla, y es la última para el día de hoy, en este ambiente, tenemos la ponencia magistral a cargo del doctor Milo Kral. El doctor Milo Kral es de la Universidad de Canterbury y recibió su bachillerato en Ingeniería Mecánica en la Universidad de Vanderbilt, en Nashville, Tennessee, y luego trabajó en General Motors en Nueva York, en la ciudad de Rochester. Volvió a Vanderbilt para obtener su máster y su doctorado en Ciencias e Ingeniería de los Materiales. El doctor Milo fue premiado con una beca de la ASEE postdoctoral en la rama de Metalurgia Física en el Laboratorio de Investigación Naval en Washington, D.C. Fue designado en la Facultad de Ingeniería de la Universidad de Canterbury, Christchurch, Nueva Zelanda, donde actualmente sostiene el rango de profesor en Ingeniería Mecánica y es el jefe de departamento. Por favor, quisiéramos recibir al doctor con un fuerte aplauso.
Thank you for the introduction. It's an honor to be here. Thank you for the organization inviting me here. Today I'm going to present two case studies on welded structures. The first is brittle fracture of a structural steel in an earthquake-damaged building. The second is the failure of a large silo. In both cases, I'll be going through the same structure, context and background, and various laboratory results, and I'll present a root cause, and finally what was done to fix the problem. The first case is the failure of a structural beam in a building in Christchurch. It's a 200 millimeter universal beam. This picture I took myself. Inside the building, looking from the inside to the outside, this is a portion of the building that has no outer wall, so you can see from inside to outside. You're no strangers to earthquakes in this country. In 2011, Christchurch was struck by a violent earthquake, and serious damage to the city, a number of deaths, and recently I understand that there was an earthquake detected in Lima on celebration of victory of Peru over New Zealand to enter the World Cup. Seriously though, this was a serious matter. The building that was affected that I'm talking about is still Christchurch's tallest building with 23 floors. On the right side of this figure is a picture taken very soon after the earthquake struck, about the middle of the day, about 1 p.m. in the afternoon. The first earthquake happened much earlier in 2010, which did very little damage to the city, but as you know from your experience, if you live in a seismically active area, aftershocks are numerous and sometimes can be worse effect than the first event. And that's what happened here. The red arrow is pointing to the building approximately, hard to see with all the dust. So again, back to this picture, this is called an eccentrically braced frame. I'm going to tell you a little bit more about what this is and what it's for. And I'm also drawing your attention to the red circle on the left that shows what's called a shear stud. They're supposed to behave in a ductile manner, as shown in the experimental EBF on the right-hand side, but this one clearly has a brittle fracture. Now, just taking a step back, modern buildings are built under a philosophy of capacity design, and that is, through the structure, damage is intentionally designed to occur at specific places, and the building is supposed to perform in a ductile manner. And ductility in a building has a different meaning than it does in our context, but in effect, plastic hinges, what they call plastic hinges in civil engineering, occur in specific locations. Now, on the right-hand side, I have a scale of magnitude of the earthquakes, and when we get into the range of 6 and higher, we accept that the buildings will be permanently damaged, and the philosophy is the preservation of life. When in actual practice, after an earthquake strikes, there is a strong and compelling reason to save some buildings that have been damaged to some extent. Now, there's always going to be some that are torn down completely, but many of the others can be repaired if the damage isn't too great. The eccentrically braced frame is one strategy for allowing this to happen, because these elements can be removed and replaced. These are lateral force-resisting systems, such that when we have a ground movement, the building reacts and damage is concentrated in specific areas in a predictable way through yielding of the ductile element. It's called an active link. This is the failed link element back in my laboratory, and then some close-up pictures. Now on the top in this figure is the top as it was located in situ, is the initiation site of the crack. The crack arrested in the lowermost flange, and so I used a simple grinder to cut away the still attached parts so that I could then cross-section this component further. A bit of a detail here, it appears that there are some arrest marks on the right-hand side that I've indicated with white arrows. Those arrest marks may have happened during events, as this damaged element was not discovered until 6 months after the major event. In order to perform the failure analysis, I cross-sectioned the initiation site, as shown here on the left, with the dashed red line showing the approximate location of the horizontal and vertical cuts. I then mounted this cross-section into a standard metallurgical mount, a 2-inch diameter mount, and performed metallography and a hardness traverse across multiple locations, and shown one location with the dashed arrowed line. Above the top part of this figure is the shear stud, and the lower part is what it was welded to, and you can see the weld microstructure at low magnification in between. Now, just again taking a slight step backward on this, shear studs are welded in situ during construction, and their purpose is to be able to fix the concrete slab above the supporting members to create a composite slab. The results of the hardness traverse, quite similar to the previous talk, were not surprisingly not overly high, but they did indicate the presence of untempered martensite, and the microstructure showed in the fusion zone and the heat affected zone the presence of untempered martensite and non-metallic inclusions. The relevant standards for the steel, the base metal, not the stud nor the weld that attaches them, are shown in highlighted in yellow. These are minimum requirements and standard, as you might not be too surprised by these, as they're historic. They're based upon experience. Energy at 0 degrees of minimum average of 27 joules, and no individual test to fall below 20. Now, since then, the standards have been raised. You can see down below the standard for grade 300 S0. It's a seismic grade. Impact temperature is to occur at 0 degrees, but now the average must be at least 70 with no individual test below 50. But the building code at the time that it adhered to was the upper one, the first one I gave. There was another problem. The origin of the steel in this building was not well documented. I was told when I started this investigation that there may have been 2 different sources of steel, and they weren't exactly sure. But the mill certification sheets that I obtained from one supplier showed very good properties, and highlighted again in yellow are the pertinent ones. The impact energy of of some of the steel in the building was reported to be well above the requirement at approximately 150 joules at 0 degrees. However, I was also supplied with the mill certification sheet for another supplier that did meet the requirements for tensile strength, but it did not report any Charpy energy. This would not have met the standard. The fracture surface, as I showed you, was quite oxidized. However, cleaning in a product called Decon 90 solution removed the oxide, and what you can see here is a textbook example of a cleavage fracture examined in a scanning electron microscope. I had the entire beam brought back to my laboratory, and I had a number of samples machined from the base metal, from the flange, and from the web. The Charpy specimens were taken from the flange on both sides, and I had 75 of these made, and a number of tensile samples also made. And I constructed this energy versus temperature plot. And this shows the data that we actually collected for this material that failed in service. And when the data is fitted to a hyperbolic sine function, the ductile brittle transition temperature, where that function equaled 27 joules, was corresponding to 11.5 degrees C, which should have been at least, at most, 0 degrees. And the energy at 0 is 12 joules. So the current minimum is 70 joules, and at the time was 27. So clearly, this confirms what we already knew, that the material had a low fracture energy at the service temperature. Now we have a problem. There are over 90 links in this building. One of them fractured. Well, there are reasons why that fracture occurred, but what we needed to do was to sort out where there might be other potential problems in this building, because clearly there had been a mistake, that some steel had found its way into active links that shouldn't have. Now we needed to find out and eliminate and replace those. It turned out that the certification sheets also showed a striking composition difference between these two suppliers in the manganese content. The manganese content of steel A is always and very consistently about 1.5 weight percent, whereas the other supplier's manganese content was around about 0.6 weight percent and quite variable. So we used a Brucker handheld X-ray fluorescence device to determine the manganese content and therefore the possible steel supplier of each one of the remaining beams in the building. And some of them were suspicious in that their manganese content was in the lower range and quite variable. So each one of those that was suspicious was tested to confirm that its Charpy energy values were adequate. This whole process was quite high profile in the city. As being the largest building in the city, or tallest, this attracted quite a bit of attention in the local newspaper. In the end, the remediation action cost in the vicinity of $10 million, but the building is back in business today. This corrective action was that once a EBF was determined to be inadequate, a new one was constructed and was welded into place. So on the left-hand side is a new one that was constructed, and on the right-hand side is it being put into its position. The root cause of this problem, as in many other incidents, required the coincidence of several things at once. Obviously, if there had never been an earthquake, this problem may have never occurred. The shear stud happened to have been located at the worst possible place, and this was at the edge of the ductile active link. The presence of that shear stud and the weld metal that attached it created an initiation site, or provided an initiation site, which allowed a crack to propagate through a low toughness material. So if any of those things hadn't happened, perhaps there might not have been a fracture, and any of this expense may not have needed to have been spent. So that's the first case study. Take a deep breath, because this one's completely different. Also, another structure, a large structure, failed. Some people have suggested the title of this talk should be "Don't Cry Over Spilt Milk," but I can tell you there were some tears shed over it. Quite a large mess was created. It was a very expensive failure, reported to have been in the vicinity of $45 million plus due to business interruption, loss of product, the replacement costs, and so on. What happened was this is one of 4 silos that is filled and emptied multiple times during the day. This one and its 3 sisters contain 500,000 liters each. So they're filled, and as the process carries on through the day to produce milk powder, they're emptied. And once they're emptied, they're cleaned, and after they're cleaned, they're refilled. This is a quite large plant. New Zealand is a leading producer of milk powder in the world, and this is one of the largest plants. Located near Invercargill, New Zealand, it's near the south end of the southern island of New Zealand. This occurred fairly recently, September 2016. There is a video, unfortunately I don't have because the company won't give it to me. I think they're afraid it'll go viral on the internet, because there is a fixed webcam pointed straight at these silos that's meant to monitor truck traffic, trucks that are bringing raw milk into the plant. And they're motion activated cameras. Well, there is a record of this event, because as the silo started to topple over, it activated this motion detecting camera and recorded the whole event. And in the video, what you can see is essentially a wall of milk coming towards the camera. It's 500,000 liters, all spilled at once. Typical silo failures, and this was a fairly unusual one, occur for different reasons. They can occur when valves don't function, when the temperature changes in an empty silo. They can crush in on themselves. In the case on the right-hand side, this is earthquake-related, when settling of the product causes a large hoop stress at the bottom of the silo. You can have this, what's called elephant's foot buckling, but that's not the case in this failure. This is a Google Maps image showing the scale of the plant. These 4 silos are responsible for only 10% of the total output of this plant, although they do in total add up to 2 million liters of product, which is filled and emptied normally twice a day. It was a complex failure site. I'll show you the dimensions of this later on, but it's a 6-meter diameter silo. And so there were in the vicinity of 18 meters of length of fracture surface to examine. I've shown these in different colors because there are different weldments that have failed. The red is what I'm going to explain this terminology in just a minute, but the red is the skirt to dome weld, and the green and blue are the first strake of the barrel to dome weld. Here's the scale image of the silo. Again, there are 4 identical ones. One of them fell over. The little figure of the person in the middle shows you the approximate scale of 20 meters in height, 6 meters in diameter. This entire structure is supported by a cylindrical skirt at the bottom, which doesn't hold milk itself. It solely supports the silo above the ground so that it can be accessed from below and emptied and cleaned properly. This and the skirt and the dome of the silo are attached by an 8mm fillet weld. The entire structure is constructed of 316L stainless steel. The failure sequence that we were able to determine after the fact was, on starting from the left-hand side, the schematic of the motion represented by the cartoons that are shown. The sequence started with the weld on the northwest side failing, which allowed the silo to start to fall within the skirt. As that happened, the silo began to lean, and as the silo dropped forward full of milk, the welds up the length of the silo failed one by one. I mentioned earlier that there are 3 identical adjacent silos, and dye-penetrant investigation showed that each of these had fatigue cracks, or sorry, I shouldn't have said that. They had cracks. In a sudden failure after 8 years of service, you can only suspect 2 possibilities. One is fatigue and the other may be stress corrosion, but most likely fatigue. But the other silos also showed signs of cracking, as shown on the figures. And here's some more evidence of the events. On the figure on the right, there's scoring marks. The scoring marks are from the silo itself falling into the skirt. So as I mentioned before, there's quite a large fracture surface to examine. I selected this area to be cut out, that's shown in red, and you can see it being lifted out from the remains of the structure on the left, about 5 meters of length of the bottom of the where the barrel of the silo met with the dome on the bottom was removed for closer examination. For example, this is a small area to look at, and a length of the weld shown here of the fracture surface, and there are faint beach marks. They're difficult to see, but there were faint beach marks, which again added to the evidence that this was a fatigue mechanism. The weld itself is irregular in geometry, and 5 to 7 meters, 5 to 7 millimeters rather, compared to its design specification of 8 millimeters. Opposite to the initial side of the failure, there was an underfilled weld. Recall that I mentioned this was an 8 millimeter fillet weld, and I've superimposed on that, not to scale image, but just to give an impression, that in places this weld was only 2 millimeters, and there was evidence in these places of tensile overload. However, most of the fracture surface revealed fatigue striations in scanning electron microscopy. The radius of curvature indicating that on most of the surface the initiation occurred from the cavity side, that is beneath and within the skirt, working its way outward. Some locations of intact welds showed other different incorrect weld geometries. For example, here, excess convexity and pre-existing cracks or crack-like defects. Here's another location showing these crack-like defects are occurring from both the outside and the inside. Well, in any fatigue investigation, it's only the beginning of the failure analysis to identify the mechanism as fatigue. The next obvious question is, what is the source of the alternating stress that drives the fatigue crack forward? There are a few obvious ones. As the silo is filled and emptied, there's a weight of 520,000 kilograms that is applied and removed. I mentioned earlier that there are cleaning cycles. The cleaning cycles cause a thermal cycle, a thermal strains that are due to temperature fluctuations from 4 degrees to 70 degrees Celsius. There's also the possibilities of the influence of wind, generating a resonance in the structure, and of course the ever-present danger of earthquakes. So let's look first at the emptying and filling. I mentioned before that there's a downward weight that induces a bending moment in the structure, shown by an analysis. The crack is sort of shown as the red wavy line. That's where the fracture occurred. Again, this is the cross-section schematic, showing on the left bottom side. I'll try to use the mouse. Is it showing up? No, I know what to do. So here, this is the skirt, and this is the dome. And to explain my terminology a little better, the dome is connected to the barrel. The fracture occurred here at the skirt to dome weld. Now, the thermal cycling, the cleaning process is called a CIP, and CIP means clean in place. There's a number of steps, but the main thing to pay attention to is that the temperature of the caustic solution that's applied is 70 degrees. The milk itself is at 4 degrees. And this model on the left is from an ASME journal that shows the results of a finite element analysis of the strains that are due to the thermal effects. This also suggests the bending moment. And again, we can analyze that wind could be in effect. This plot on the left-hand side shows the prevailing winds, their frequency, and their velocity historically. And on the right-hand side is a map of earthquake activities over 10 years. And remember, again, we're talking about the location of this plant being down in this location of the country. The entire country is seismically active. So all up to this point is a certain amount of speculation. There's nothing better than going out and getting the actual data. And so we instrumented one of the remaining silos with strain gauges, as shown in multiple locations. And these strain gauges measure strain at 0 degrees and plus and minus 45 degrees. This is a pretty complicated graph, so I'll go slowly. On the left-hand side, figure A shows the strain gauge response with the process cycles. So there are 3 strain gauges, as I mentioned before, or in one strain gauge there are 3 axes, 0, minus 45, and plus 45, and those are shown as 3 different traces in color. And you can see that they peak at maximum values on the negative minus 800 microstrain and plus 800 microstrain at different times. After this incident, the company decided they would only fill these silos until the problem was resolved. They would only fill them with 250,000 liters. So this is the strain obtained at 50% of the fill. On the lower left-hand side, the plot indicates the level of milk. So we go from 0 to 250,000 liters in blue, and on the orange trace, that's the temperature trace. So that first we fill, then we empty, then we CIP in time, and then we repeat. And these process events match perfectly with the strain data. So the strain amplitude at 100% fill would be double those values approximately. And so we have a strain amplitude that varies between minus 0.16 and 0.08 millimeters per millimeter. I also attempted to do striation counting to try to match that to close the loop on this process. Now there's a lot of scatterness data, as you can see on the right-hand side. It's difficult to actually do this in actual service components. It may be easier in laboratory components, but in service, not so easy. However, I fitted the data to an exponential function and integrated over 1 to 8 millimeters and determined that that would be in line or consistent with process cycles that occurred over the entire service life, 8 years, 2 cycles per day, 200 days of operation per year. That comes to 3,200 cycles. Now, this may be a coincidence, but at least it is consistent with the fracture surface. And note that this requires a 1 millimeter pre-existing defect, which means there would be no initiation period, or that would be insignificant. Whereas most of the time in fatigue, initiation period consumes most of the life. In this case, with a pre-existing defect, that's not necessary. There are applicable standards to this, and just for your reference, the top right-hand figure shows the subject schematic. This is also a known problem. I was able to find 2 US patents that addressed this problem specifically. And having been told by the management of the company that this event had never happened before, this may have come as a bit of a surprise. But these are quite old. This one is from 1961 and shows that this is a design that has been patented to address this problem of thermal gradients that cause fatigue. There's another one showing how we might address this problem, thermal cycling, that causes fatigue. So, in conclusion of the second failure analysis, obviously the silo failed when it was full. The failure mechanism is consistent with bending fatigue, and some places reversed bending fatigue. It was consistent with the process cycles rather than environmental effects, most likely almost entirely due to filling, emptying, and cleaning, and repeat. It was clear in examining the weld that the weld as it was manufactured did not meet the design drawings, and that it contained pre-existing crack-like defects. So evidently and clearly this weld is fracture critical, and for continued safe operation there need to be periodic inspections or some kind of revision to the design to make sure we have fracture safe operations, because it was only pure luck that no one was hurt in this accident. And overall, this silo design is inherently difficult to manufacture, and because the weld is fracture critical, it needs to be redesigned. Overall, my observations from these 2 case studies, both of these involved failure that was initiated at welds. In both cases, these welds had pre-existing defects that caused that were near the root cause of the failure. However, the true root cause is, in both cases, design and manufacture. So, I'd be happy to take any questions. Thank you.
Si el público tiene alguna pregunta. Sí, por favor.
Hi, it's about your first work with steel with manganese. I had some problems. Looks like the failure. We made some research and we get a better relationship with the ratio manganese carbon instead only manganese. And we got also some points out of the behavior. We made some measurement of the grain size. In your job, you make some characterization of the Microstructure of the high manganese steels?
No, that's a very good question. Though I did not attempt to make any microstructural correlation with the fracture properties, but that's a good point. Yeah, thank you.
Only to reverse. We found some critical failure only in the test in pipe according to ASME V31. In new pipes, only in the pressure test blow out. When all of the manufacturer has ISO 9000 and so on, so different providers, Asia, European, and USA. And all of them has certified products, but in the field, blowouts. And we found your relationship. High manganese is good for Charpy nose, but some points out of the behavior. And the answer was a huge grain size.
Okay.
So now, actually, I'm doing a research with Pancho Rumiche, looking for a technique to measure the capability of the impact steel, measuring the chemical composition like you did with the XRF machines. And the another side, look for the grain size and high manganese steel. Thank you for that.
Thank you.
¿Otra pregunta? Entonces, si no hay más preguntas, un fuerte aplauso para nuestro invitado especial, por
Thank
favor. Y solo nos queda cerrar el día de hoy las actividades y invitarlos para mañana a las 9 de la mañana, que se inician las últimas actividades del último día del Congreso. Muchas gracias por su atención. Hasta luego.